Edge AI matters when models have to run close to the data source, with limited power, memory, and network access. The focus here is how those constraints shape real systems and the design choices that make them work. Deployment shape is the first question in Edge AI. Build for the device from scratch, or fit intelligence into something that already exists. That choice changes the model, the hardware, the power budget, and the amount of compromise the system can tolerate. Edge AI becomes a hardware question when raw sensor data is too large, too expensive, or too power-hungry to send away. The real design problem shifts from whether AI is possible to where the computation should happen. A useful way to think about that choice is to separate projects into two families. One starts fresh, and the other has to work inside an existing product. Greenfield means the edge device is part of the plan from start. The team can shape the hardware, the model, and the power limits together instead of trying to force them into separate decisions later. That is hardware-software co-design. Compute, memory, sensors, wake-up behavior, and model size are chosen as one system, so the final device is built around the job it needs to do. The advantage is fit. If the device needs always-on listening or local classification, the platform can be built to support that behavior efficiently. Nothing has to be oversized or patched in after the fact. The cost is that more decisions happen early, and more money goes into new hardware before the market has proven the idea. When a use case is clear and the limits are tight, that upfront investment can pay off in a system that works cleanly instead of just barely working. A wake-word assistant designed from scratch shows the pattern well. The microphone path, the sleep states, and the processor are chosen together so the device stays responsive without draining the battery. Brownfield starts with an existing device or an installed fleet, so the challenge is adaptation rather than invention. The new intelligence has to live inside old limits and preserve the original product while it gains new behavior. That usually means working around fixed memory, limited processor headroom, battery constraints, and certification rules you do not want to restart. The design space is narrower because the hardware already has a job to do. Brownfield lowers the cost of inventing a new device, but often forces compromise. A firmware update may be enough to add a feature, yet the result is usually good enough rather than ideal. A headset with spare processor cycles and an existing audio path may pick up wake word detection without new hardware. The intelligence changes, but the physical device stays the same, which is the classic Brownfield trade. The same pattern shows up in sensor-heavy wearables. Raw readings can be too expensive to transmit, so the device summarizes or classifies them on board and sends only the useful result. Riverwatch Node shows how the same goal can be easier or harder depending on the starting point. Built Greenfield, the team can choose sensors, power management, and communication together. Built as a retrofit, it must adapt to the enclosure and radio that already exist. The practical difference comes down to four forces that shape every decision. One path gives freedom, the other gives continuity, and each favors a different kind of engineering trade-off. That distinction matters because it reaches into the model, the hardware, the schedule, and the business case. Once the deployment path changes, the whole project changes with it. Greenfield gives the team room to optimize the whole system at once. Brownfield gives the team a way to extend what already works without starting over. A fresh design can be tuned as a unit, so it often performs better. A retrofit can lean on an existing fleet and supply chain, so it often reaches the real world faster, even if the technical solution is less elegant. That is why the deployment path is not a side issue. It determines how aggressive the optimization can be, how much on-device processing is realistic, and how much failure the business can survive. Product teams need people who can judge whether a feature belongs in new hardware or must be forced in old hardware. Model accuracy matters, but constraint awareness matters just as much, especially in brownfield deployments. That becomes the lens for everything that follows. Once the starting point is clear, the design choices make sense. Some edge AI systems are natural fits for the edge, and others are clever retrofits that survive only because the team understood the constraints. Edge AI work usually starts by asking whether the device is being designed from scratch or adapted later. That difference changes the hardware, the software, and the kinds of trade-offs that matter most. The turning point is physical, not abstract. Once a device can collect data more easily than it can send that data off-site, the first analysis often belongs on the device itself. Microphones, cameras, vibration sensors, GPS chips, and similar hardware can produce far more data than a network link or battery can comfortably handle. That forces a practical question. Where should interpretation begin before the full stream ever leaves the device? Those are the two basic paths. One starts with a blank sheet and designs around the edge task. The other keeps an existing product and tries to add intelligence without upsetting the rest of the system. A Greenfield project lets the team choose the sensors, processor, firmware, battery budget, and enclosure as one design problem. That is hardware and software co-design, because every part of the product is aligned to the model it needs to run. A brownfield project begins with limits that already exist. The device is already shipping, so the model has to fit the memory, power, timing, and update rules of the old system rather than replacing them. That difference changes the goal. A new design can be tuned for ideal sensing and inference, while a retrofit has to work with the processor, sensors, and firmware the product already has. The reason local inference matters is simple. Many devices collect more data than they can afford to send elsewhere. The useful move is to turn a continuous stream into a small number of events that matter. A wearable can sample motion all day, but uploading every reading would waste battery and bandwidth. A field device can watch for a vibration pattern or a sudden change and only speak up when something unusual happens. That is why local processing is a product decision, not just a networking decision. If the device can classify what matters on site, it can send an alert, a label, or a summary instead of raw data, which makes the whole system faster and easier to trust when connections are weak. Wake-word detection shows the split very clearly. The same task can feel natural in a device designed for it, or cramped in a device that has to be upgraded later. The device has to monitor audio all the time, yet it should act only when the right phrase appears. That makes the task a perfect example of constant sensing paired with selective response. A phone designed from the start can reserve low-power listening, memory, and signal processing for that task. The model can run continuously without forcing the main processor to stay fully awake, so the whole product is shaped around that behavior. An existing Bluetooth headset usually was built for calls, pairing, and noise reduction, not for a voice assistant workload. Adding wake word support may still work, but the model, update process, and user experience all have to fit a tighter box. The feature may look the same on the surface, but the engineering story is different. In one case, it is part of the design. In the other, it is a compromise that has to earn its place. A remote sensor station makes the same lesson visible in hardware. The important details are the limited power, the weak connectivity, and the need to make decisions locally instead of streaming everything away. A weather station or similar device may sit where power is scarce and connections are unreliable. In that setting, a small model that detects a threshold, a pattern shift, or a fault is often more valuable than a raw log that arrives late or never arrives at all. That scarcity is the real driver behind many edge AI products. They exist because the device has to work inside hard physical limits, not because local inference is a trendy idea. Once the design path is clear, the trade-offs become easier to see. Greenfield opens room for optimization, while Brownfield opens room for reuse, but each one also closes off some options. With a clean slate, the team can pick the best sensors, reserve compute for the model, and shape the battery and enclosure around the workload. The cost is time, capital, and the risk that the new product may not land as planned. A retrofit can modernize an installed product without rebuilding everything from zero. The trade-off is that old chip choices, old firmware assumptions, and imperfect sensors still shape what the AI can realistically do. That one question tells you what kind of engineering effort is ahead. It also shows whether the team needs model skills only or a broader mix of hardware, firmware, sensor, and power expertise. This split is useful for reading roles as well as products. Different jobs ask for different combinations of new device design, retrofit skill, and low-level system knowledge. A greenfield role may sound more ambitious, but a brownfield role often has the tougher constraints. The engineer has to improve the product without breaking what already worked for customers. Job descriptions often reveal the direction of the project. Requests for embedded ML, firmware awareness, and low-power tuning usually point to a retrofit, while requests for sensor selection and end-to-end architecture usually point to a new build. That simple distinction becomes a lens for the rest of the topic. Once you can tell whether a product is being built fresh or adapted in place, the larger families of edge AI devices are much easier to place and understand. Edge AI becomes concrete when a product has to make useful decisions outside the comfort of the cloud. The focus here is on the constraints that shape real devices and why local inference often becomes the practical choice. The core idea is that a device is no longer just collecting data, it is acting on it where the decision has to happen. Once timing, power, and connectivity become part of the problem, the design choices start to matter in a very concrete way. A good way to understand edge AI is to begin with the operating conditions. If a device has weak connectivity, a tiny battery, or a hard real-time requirement, the model architecture matters less than whether the system can function reliably in that environment. That shift matters because it changes the question from how accurate is the model to what has to work in the field. Once deployment constraints dominate, edge AI looks less like a research topic and more like a systems problem. A remote monitor is a good example of the pattern. It watches locally for a fault or unusual vibration, then sends only a small alert when something crosses a threshold, which saves bandwidth and protects the system when the connection is unreliable. Those trade-offs repeat across many products. When data is expensive to move, slow to transmit, or sensitive to expose, processing it on the device is often the cleanest way to keep the system usable and safe. A few deployed products are enough to show the pattern clearly. The point is not the number of examples, but the fact that the same design logic shows up in very different settings. Even a small set of fielded devices makes the idea visible. Once the same constraints appear again and again, the field starts to look less abstract and more like an engineering response to reality. A monitoring device on infrastructure, a wearable in hazardous work, and a wildlife tracking collar all solve different problems, but the mechanism is similar. Each one turns noisy input into a small decision near the source, because sending everything upstream would waste energy and delay the response. That common design move cuts across markets and sensor types. Whether the device is watching machines, people, or animals, the winning strategy is usually the same. Keep the raw data local, preserve battery life, and accept limited communication as part of the job. At this point, more examples would not help as much as structure. Grouping the products by the kind of problem they solve gives a clearer map of the field than listing one device after another. These examples are representative, not exhaustive, and they point toward a useful map. Object tracking, system monitoring, people and living things monitoring, and signal transformation. That map matters more than the model family, because deployment is driven by the problem and its constraints. The work sits between several disciplines at once. A practical edge system depends on sensors, power, firmware, deployment limits, and the behavior of the finished product after it leaves the lab. So the job is about making intelligence durable in the field. The main point is that edge AI is not waiting for a future use case. It is already in products because cloud-only designs often fail the demands of real deployment. From here, the useful step is to sort those products into application families so the field becomes easier to navigate. Real deployments make edge AI concrete because they show where local intelligence solves real constraints. The examples that follow all share the same pressure: limited connectivity, limited power, and the need to act before a distant server could respond. A useful way to understand edge AI is to examine products already operating outside the lab. The important part is not whether the user notices the AI. It is that the device has to make useful decisions right where the data appears, under messy conditions and tight resource limits. Infrastructure monitoring shows why speed and resilience matter more than perfect connectivity. When the network itself is unreliable, the device has to make the first judgment on site and only ask the cloud for help when the situation really needs it. A power line monitoring system is a strong example because delay can turn a fault into a much larger hazard. The device cannot depend on constant connectivity, so it needs to detect meaningful changes locally and raise an alert before the problem spreads. That design choice cuts bandwidth use and keeps response time short. The system sends out only the event, the classification, or a short clip when something matters, which also makes the deployment more reliable when the link is unstable and the hardware has to survive harsh outdoor conditions. Wearable safety devices bring a different constraint into focus. The user is already busy, moving, and often in danger. The device has to do its analysis quietly and fast enough that the wearer does not have to stop and think about it. For firefighters or first responders, the device may be tracking posture, temperature, or motion, and that judgment has to happen on the body itself. A remote system would be too slow and too easy to miss when the environment is chaotic. The wearable has to fit the job physically as well as computationally. It must alert immediately when conditions become unsafe, conserve battery by avoiding unnecessary uploads, and stay comfortable enough to disappear into demanding work. Wildlife tracking adds a long-range power problem. When the device is strapped to an animal in terrain that is hard to reach, the system has to spend its energy on observation rather than constant communication. A collar for elephant tracking has to work for long periods with very limited maintenance. If it streamed raw data continuously, the battery would drain quickly, and the field researchers would lose the chance to collect useful information over time. Local processing changes the balance. The collar can detect movement patterns on device, keep only the events worth studying, and send smaller summaries whenever communication becomes available, which saves energy and reduces noise in the dataset. These cases look different on the surface, but they push design in the same direction. Each one rewards computation close to the source, selective communication, and a careful respect for latency, bandwidth, energy, reliability, and privacy. That pattern is the practical version of the blurb trade-off. When the environment is harsh, the best system is often the one that sends less, waits less, and depends less on perfect connectivity. The range of devices matters because it prevents a narrow view of the field. Edge AI is not one market in disguise. It is a way of placing intelligence wherever physical constraints make centralized processing a poor fit. A useful taxonomy turns scattered examples into a structure you can reason about. Once products are grouped by the problems they solve, it becomes much easier to think about how Edge AI turns model capability into systems that still work when the lab conditions disappear. Object tracking at the edge is about watching physical things over time and turning change into useful action. The important idea is not the industry label, but the need to notice movement, loss, drift, or condition changes and react before the situation gets worse. That pattern shows up anywhere a device has to understand state across time. The sensor may be looking at a package, a shelf, a vessel, or a remote site, but the job is the same. Detect meaningful change and turn it into something the system can use. Those questions are the heart of the problem. Edge systems often care less about raw measurements and more about whether something important happened, because that is what lets them track the real state of the world over time. Once a device can turn a bump, a missing item, or an abnormal drift into an event, the rest of the system becomes much easier to manage. It can alert, log, or escalate only when something matters instead of storing every signal forever. Local inference changes the whole architecture because the device can decide on-site instead of waiting for the cloud. That matters when the network is weak, the radio is expensive, or the device has to keep working even when connectivity disappears. A shipment monitor is a good example of that design. It learns normal transport behavior from accelerometer and GPS data, then logs only the incident details when handling looks wrong, so the device can keep working whether the network is available or not. That choice saves bandwidth and energy at the same time. A short report is cheaper to transmit than a constant stream of samples, and the system stays useful even when the link is unstable or missing. Those trade-offs drive the design. Some deployments are constrained mainly by bandwidth or battery life, while others care more about offline reliability or privacy. So the right solution depends on the actual operating conditions. The shipment monitor is only one case of a much wider pattern. The same local observe, local interpret, compact report structure appears wherever edge devices need to track objects or events in the physical world. Retail systems can watch shelves for replenishment needs. Environmental systems can spot debris or other objects of interest. Maritime systems can flag hazards or route deviations. And sensing sites can report likely event from vibration or signal changes. The sensor type changes, but the pattern stays the same. That structure scales well because it keeps the device focused on the decision, not on shipping every raw measurement upstream. It also sharpens the modeling problem. The question becomes what the system needs to know, not just what the sensor happened to record. Privacy can be part of the architecture rather than an afterthought. When a device sends only stock exceptions or hazard alerts, it can reduce the amount of sensitive raw data that leaves the site. That matters in places like retail, where the goal may be inventory visibility rather than worker monitoring. Edge processing can narrow what gets transmitted, which helps keep the system aligned with the purpose of the deployment. The same idea can support workplace safety or other settings where only exceptions need to leave the device. Still, privacy is not the only concern in every project, so the design has to balance privacy with cost, safety, and resilience. For builders, the lesson is practical. Edge object tracking often succeeds or fails on system design, not just model accuracy. The strong solution is the one that fits the sensor, the environment, and the network conditions it will face outside the lab. Teams need event-driven sensing systems that account for power limits, positioning, storage, and unreliable connections. A model that looks good in a notebook can still fail if it assumes perfect upload or ideal field conditions. Selective attention is the core idea. Detect what matters, ignore the rest, and move only the useful information when the real world and the network do not cooperate. That is why this pattern lasts. It matches how edge systems actually have to operate. Object tracking at the edge is about keeping physical things legible as they move, change, or fail. The value shows up when a system has to preserve evidence, detect problems early, and work even when connectivity is unreliable. Once the focus shifts from the device to the physical process, the use cases become much clearer. Packages move, doors open, shelves empty, and sensors drift out of place. So the real job is to notice those changes while they happen or keep enough evidence to reconstruct them later. That broader view explains why this pattern shows up in shipping, retail, environmental monitoring, marine safety, and geophysics. The object might be a box, a vessel, a shelf, or a buried instrument, but the same challenge remains. Capture what changed, turn it into usable signals, and keep the important record close to the edge. The first step is turning raw sensor readings into something the system can act on. That is where the data stops being just measurements and starts becoming state, events, and decisions. Different sensors reveal different parts of the story. Accelerometers catch shock and vibration. Cameras show position and occupancy. Radar can detect movement and poor visibility, and environmental probes report conditions such as temperature, humidity, or gas concentration. The important step is local interpretation. The edge system decides whether something meaningful happened, like a threshold crossing, tampering, spoilage, or a device going out of range, and only then chooses what evidence deserves to be kept or transmitted. A shipping package makes the trade-offs easy to see. With a small sensor unit, the system can watch for impacts, vibration, temperature swings, and route changes without needing to stream every raw reading to the cloud. That kind of device keeps a local record of the moments that matter, along with time and location. When the connection is available again, it sends summaries instead of a constant flood of raw sensor data. This design handles the messy reality of transport networks. Warehouses, tunnels, ports, and dead zones no longer break the history, and the log still gives a clear forensic trail if damage is reported after delivery. That is the practical payoff of the bandwidth, power, and reliability trade-offs. Edge processing turns continuous raw data into a compact event record, which is cheaper to move, easier to store, and often the only sensible way to preserve evidence at scale. The same pattern appears in retail, but the reason shifts from shipment reliability to privacy and scope. Shelf monitoring can track stock levels and product movement while avoiding continuous export of detailed footage from a public-facing space. The goal is not to watch shoppers. The goal is to detect empty shelves, movement, or planogram problems, and send only the narrow inventory signal that the store actually needs. That narrowing matters because it reduces the privacy burden of the system. Local processing lets the designer discard most of the footage and keep only counts or events, which makes the deployment feel more proportionate and less like surveillance. The same pattern reappears wherever the world changes faster than the network can report it. The device sits close to the change, and the job is to preserve the right evidence without depending on constant cloud contact. That is why this approach fits environmental stations, marine monitoring, and geophysics so well. When power is scarce or connectivity is weak, the system has to log conditions locally and keep working until the data can be recovered later. Builders keep returning to it because it solves field problems, not lab problems. It demands sensors that survive the environment, local models that detect the right events, storage that preserves evidence, and communication that can tolerate delay. That combination is the deeper lesson. Edge object tracking works because it joins local inference, compact logs, intermittent connectivity, and selective disclosure, which often makes it a better fit than a cloud-only design before the product even leaves the lab. Systems become the focus when the goal is not just to observe data, but to keep a machine, network, or environment behaving safely and reliably. The target is the running process itself. The model watches what is happening, detects change, and supports decisions that affect the system in real time. This kind of edge AI sits inside an ongoing process where the signals keep arriving and delay has a real cost. A model may be watching a machine, a vehicle, a building, or a network. And the important part is that the response must come while the situation is still unfolding. Monitoring means understanding the state of the system from its signals. Control goes one step further by acting on that understanding, and Edge AI often sits between the two by turning noisy measurements into timely alerts, summaries, or shut-off signals. The same pattern appears across many settings, because the technical need is similar even when the industry is different. Factories use it for motors and production lines. Transport uses it for vehicles and fleet health. Homes use it for safety and appliances, and warehouses and networks use it for fast detection without sending everything off-site. The shared design logic is simple. The world does not pause for a cloud round trip. These systems have to keep observing, keep responding, and keep working even when the connection is slow, expensive, or unreliable. Predictive maintenance gives the cleanest example of this idea because the value is easy to see. Catch failure early enough to prevent downtime and damage. The model is looking for weak signals hidden in noisy sensor data, like small changes in vibration, temperature, sound, or power use. Those shifts may look minor on their own, but together they can show that a part is drifting toward failure. A remote oil rig makes the trade-off clear. Raw data can be abundant, but bandwidth may be limited. So the better design is to analyze the stream close to the equipment, compress the result into a health summary, and raise an immediate alert when trouble is likely. That is the practical value of Edge AI here. It converts constant sensor noise into information that operators can act on quickly. Local inference fits this setting because the data never stops. The useful signal is buried inside noise, and moving every sample is often the wrong trade-off. A sensor stream is not a neat single input. It arrives all day, and sending everything upstream burns bandwidth, adds latency, and creates a dependency on network quality and remote uptime. Local processing bundles several benefits together, so the same design choice improves both the technical system and the operating cost. Filtering and summarizing at the edge means only important events leave the device, which keeps the network from filling up with raw measurements. When analysis happens where the data is produced, the device can react immediately instead of waiting on a round trip to a distant server. If the connection drops or gets weak, the local detection logic can still keep running, which is crucial in remote or unstable environments. Sending and storing every sample is often more expensive than sending only the events that matter, especially at scale. Keeping sensitive operational data on device can also lower the chance of exposing employee activity or facility behavior that does not need to leave the site. Those five pressures line up in the same direction. Bandwidth, latency, economics, reliability, and privacy all favor on-device inference when a system is large, fast-moving, or remote. A useful mental model is to separate seeing from acting, because not every monitored system should be controlled automatically. Sometimes the output is just an alert or a maintenance ticket. Other times the edge model triggers a local action, like throttling a motor or isolating a network segment. And the key is to do only the amount of work that keeps the system safe and responsive. Once the model can influence the system, mistakes matter more. False alarms interrupt work, missed warnings cause damage, and overly aggressive automation can create a new failure. That is why thresholds, fallback behavior, validation, and human oversight matter so much. The work often sits at the intersection of models and operations, where the goal is to keep real systems running well under real constraints. Jobs in industrial IoT, manufacturing, logistics, robotics, and reliability engineering are usually judged by uptime, safety, and reduced service cost. People in those roles need to understand sensors, deployment conditions, alert design, and the consequences of a wrong decision. That is why this category matters for edge AI careers. The best builders can reason about maintenance windows, site connectivity, failure modes, and the cost of delayed action, not just prediction scores. The main decision rule is simple. When a system must be watched continuously, answered quickly, and protected from cloud delay or cloud risk, local inference becomes the right tool. Predictive maintenance on a remote oil rig makes the idea concrete. The edge device absorbs the noisy stream, spots change early, and produces fast alerts or control suggestions even with a weak network. That same logic carries to transportation, homes, warehouses, and security systems, because when a machine matters, the delay matters too. This part focuses on how Edge AI helps us understand real systems while they are running and how that understanding can sometimes drive immediate action. The important idea is that the model is not just recognizing patterns. It is helping a machine, vehicle, or network behave better in the real world. The map here is practical. what kinds of problems appear in industry, why the edge matters, and where prediction or control becomes necessary. That gives us a way to sort applications without getting lost in abstract labels. Many useful edge AI tasks start with a system that is changing over time, a machine warming up, a vehicle drifting off schedule, or a robot behaving strangely. The device at the edge watches local signals, turns them into meaning, and may act before a cloud service could respond in time. A helpful way to organize these problems is by function. The same deployment may monitor, predict, detect anomalies, and sometimes control the system, but those jobs are not identical. Monitoring keeps track of what equipment or infrastructure is doing right now. The point is awareness, knowing the present condition well enough to notice change. Prediction pushes that awareness forward. Instead of only reporting the present, it estimates likely wear, drift, congestion, or failure before those outcomes fully appear. Control goes beyond observation and uses the model's output to change what the system does. A feedback loop matters here because the response has to improve the situation rather than just describe it. Anomaly detection looks for behavior that does not fit the expected pattern, that can point to faults, intrusion, misuse, or unsafe conditions, even when the exact failure mode is not yet known. These four tasks fit together. Monitoring tells you what is happening now. Prediction tells you what may happen soon. Anomaly detection tells you when the pattern has gone off course. And control uses that information to change the outcome. Some systems only need an alert, while others need a response in milliseconds. That pattern shows up in many places, from industrial maintenance to fleet systems and robotics. The sensors differ, but the logic stays the same. Noisy signals come in, a local model interprets them, and the system records, warns, predicts, or acts. The edge becomes the right choice when a system needs local observation and a fast response. Several recurring constraints push deployment away from the cloud and toward on-device inference. The edge matters here because the job is not just to analyze data after the fact. The model has to stay close to the system so it can react under real operating constraints. Latency is the first pressure. If a machine overheats or a robot needs immediate correction, a round trip to the cloud can arrive after the decision has already become critical. Bandwidth is the second pressure. Continuous sensor streams are often too large to ship, so the local model condenses raw data into a few meaningful events like fault likely or threshold crossed. Reliability is the third pressure. Remote or harsh environments often have unstable connectivity, so a model that depends on constant network access is fragile from the start. Economics is the fourth pressure. Streaming, storing, and reviewing everything is expensive, so edge inference lowers costs by filtering data close to where it is produced. Predictive maintenance brings the whole pattern into focus. It combines business value, operational risk, and the need for early warning in one concrete setting. The value is easy to see. Catch trouble early, schedule service before damage spreads, and replace parts before a small problem turns into a bigger one. That is where edge inference can save both time and equipment. A remote facility makes the pipeline concrete. Vibration, temperature, pressure, acoustic signals, and motor load all stream in, but only a small part of that data really signals a change worth acting on. Once the signals are flowing, the question becomes how they move through the system. The useful structure is a simple pipeline from sensing to decision. Each step narrows the data into something useful. Sensors produce the raw stream. The local model interprets it, and then the system turns that interpretation into an alert or a recommendation that a human or controller can act on. That is the real advantage of the edge. The whole loop is built around the conditions of the site. If the network drops or the asset is remote, the inference still runs, and the early warning still arrives in time to matter. The important distinction now is between observing a system and changing it. Those two roles sound close, but they demand different levels of trust in the model. Monitoring means watching and reporting. Control means acting on the system itself, so the model's output changes behavior instead of only describing it. A defect detector is monitoring, while a robot that slows for a nearby person is control. Once the model sits inside a feedback loop, speed, accuracy, and stability all matter, because a bad response can make the system worse. That is why these applications are not only about efficiency. A well-designed system reduces wasted motion, shortens response time, and protects people and equipment, while a poor one can hide failure or react too aggressively. A compact way to judge the case for edge deployment is blurb: bandwidth, latency, economics, and reliability. Those four pressures often explain why the model belongs at the source. This acronym gathers the main deployment pressures into one frame. If any of these are strong, the edge starts to look less like an option and more like the natural place to run the model. Bandwidth favors local processing when the raw stream is too large or too continuous to send elsewhere. The goal is to summarize first and transmit only what matters. Latency favors the edge when timing is critical. If the system has to react right away, even a small delay can make the decision too late to help. Economics favors local processing when transmitting, storing, or manually reviewing all the data costs more than summarizing it near the source. That is often true in large-scale deployments. Reliability favors local processing when the network is unstable, unavailable, or too expensive to depend on. A deployable system has to keep working when the link gets weak. Predictive maintenance is where all four pressures often appear together. A remote or time-sensitive operation may not just benefit from edge AI. It may actually depend on it. These ideas map directly to real work in industry, robotics, fleet systems, and security. The job is not only to build a model, but to understand sensors, constraints, and operational consequences. Employers want people who can connect the model to the actual environment it serves. That means understanding sensors, failure modes, maintenance workflows, thresholds, and what a useful response looks like in practice. Reliability and safety are not extras here. They're central requirements. If the model misses a fault, raises too many false alarms, or behaves unpredictably, the cost can show up immediately in the operation. A simple question helps decide when edge AI belongs in the design. If the system needs local awareness and local response, the edge is probably the right place to solve it. When the problem involves machines, vehicles, networks, or other complex systems, ask whether the decision has to happen where the system lives. If the answer is yes, edge AI is likely part of the solution, especially when sensing is noisy, connectivity is weak, and failure is expensive. People, animals, plants, and living environments change the deployment problem because the signal is never still for long. The rest of this topic is about why that movement pushes computation toward the edge. A machine often gives a stable input, but a living target does not. Faces turn, bodies move, plants sway, and sensor readings can change fast enough that a delayed cloud decision misses the moment that mattered. The main issue is timing and sensitivity. Once the target is alive or context-dependent, the system has to react locally to motion, change, and sometimes privacy concerns before the data loses value. These use cases look different on the surface, but they share the same pattern: continuous sensing, fast change, and decisions that depend on context. That is why they keep showing up in edge AI discussions. If every raw signal has to travel first, the system pays in delay, network cost, and exposure of data that may never need to leave the device. For human-facing products, that extra collection can make the design feel intrusive even when the intent is harmless. A wake word assistant is a good example because the device can listen locally for one narrow trigger and stay quiet otherwise. That restraint matters as much as efficiency, since people are much more willing to trust a device that filters locally than one that sends every ambient sound away for inspection. The benefits split into two practical reasons: protecting privacy for people-facing systems and making remote sensing work where connectivity is weak or expensive. One reason is about exposure, and the other is about independence. Local processing can shrink what leaves the device, while also letting the device function when a network is not dependable. Continuous sensing may be necessary to catch a voice cue, a gesture, or a medical event, but that does not mean the raw stream should be shared in full. When the device turns a stream into a small event or a simple yes or no decision, it reduces who can see the sensitive data and for how long. Far from reliable connectivity, The device has to do more of the work itself. It filters noise, detects the useful moment, and keeps only what is worth sending, which makes Edge AI a practical necessity rather than a convenience. A field monitor in a remote habitat shows the pattern clearly. When a site is hard to reach and the data is messy, local filtering cuts storage waste, avoids needless trips, and gets the important observation to people sooner. The same deployment logic appears across several categories, even though the sensors and environments differ. The point is to keep the pattern compact and recognizable. Each example below uses the edge for the same reason. It helps the device decide locally which moments matter and which ones do not. Wearables and assistants have to watch all the time, but they should expose only a tiny result, like a detected activity or a trigger word. That keeps the system responsive without turning the whole stream into shared data. In safety and healthcare settings, the value of the signal drops fast if the decision comes late. A local model can flag the event while it still matters clinically or operationally. Security systems need to notice presence or motion without sending every frame upstream. Local interpretation keeps the server from becoming a dumping ground for raw surveillance data. Agriculture and environmental sensing depend on conditions that shift with weather, sunlight, season, and location. Edge processing helps the device keep up with those changes instead of waiting for a distant system to sort them out later. Wildlife monitoring adds distance and field cost to the problem. The device has to make the first judgment on site because hauling back every recording is slow, expensive, and often unnecessary. The sensor type is not the real point. What matters is that the deployment has to interpret locally first because the target changes quickly. The data may be sensitive or the site may be too remote for a cloud-first design to work well. Wildlife monitoring shows the full trade-off clearly because storage, distance, and weak connectivity all hit at once. That makes it a clean example of why edge processing is not just helpful, but often the only workable approach. A camera trap in the field does not mostly capture dramatic animal activity. It captures wind, shadows, vegetation, and repeated almost identical frames. If every frame is kept, the device wastes space, and the people reviewing it waste time. Once the device can recognize useful moments on its own, it can store far less and send back far more value per byte. Researchers get the appearance of a target species or a change in movement without sifting through hours of irrelevant footage. A river monitor follows the same logic in a different setting. When the signal is messy and the site is hard to reach, filtering on the device is what turns raw data collection into something operationally useful. The practical skill is translating a sensing problem into a system that can actually be deployed. That means matching the model to the environment, the network, the privacy limits, and the failure modes that are acceptable. Good edge work is not only about model accuracy. It is about deciding what must happen on the device, what can wait, and how the result stays privacy-aware in human settings or connectivity-aware in remote ones. The final question is not whether the cloud can process the data, but what must be understood immediately and locally with minimal exposure of raw signals. Living systems are dynamic, time-sensitive, and often privacy-sensitive, so the deployment context matters just as much as model quality. Edge AI fits when local interpretation is the safest, fastest, or most realistic way to understand what is happening. That sets up the broader map that follows, where these human-centered and biological applications get grouped by the kind of edge problem they solve. This part is about where edge AI becomes useful in the real world, systems that deal with people, animals, plants, and other living environments. The important thread is that these settings demand quick decisions, careful handling of data, and clear limits on how information is used. Human and biological sensing becomes concrete when a device has to act on what it detects right away. That is where local processing starts to matter, because the value comes from turning a signal into a decision at the moment it happens. A person, animal, or plant does not produce clean, steady data. The signal may change quickly, carry noise, and depend on context, so delay can destroy its value. Edge AI fits well here because the device near the action can interpret the signal immediately instead of waiting for a distant server to catch up. The same pattern shows up across many settings: a home, a clinic, a farm, or a wildlife site. The device is not just storing data. It is deciding what matters enough to keep, act on, or send onward, and that choice is what makes the system useful. Local inference earns its value whenever the system has to respond close to the event. In human-facing devices, that often means privacy and speed. In sensing systems, it also means a better balance between what stays on the device and what leaves it. A wake word detector is a good example of selective listening. The device must monitor continuously so it can notice the activation phrase, but most of the audio never needs to leave the device, which keeps the system responsive while protecting everything that happens around the wake word. Wearables depend on fast local interpretation because the user may need an answer even when the phone is away or the network is down. The same idea matters in healthcare too. The device can spot movement patterns or biosignals quickly, and keeping sensitive data local helps preserve trust. Safety and security devices work better when they can recognize an event without streaming everything all the time. That saves bandwidth and lowers dependence on a perfect connection, but the deeper benefit is resilience. The system can still notice a fall, intrusion, or hazard when the network is unreliable. Remote wildlife observation depends on the same logic under harsher conditions. A camera trap may collect mostly empty images, so filtering out blank frames or irrelevant species on the device saves effort and makes a hard-to-connect location much more practical to study. Agricultural systems often run where connections are intermittent or expensive. Local inference lets a sensor or livestock monitor detect stress, motion, crowding, or environmental change on site, then send only the important events or summaries instead of waiting for perfect connectivity. Three forces keep pushing these applications toward local processing. Each one points to the same conclusion. The device near the event is often the most practical place to make the decision. The argument is simple. Some systems need to react fast, some cannot afford to move huge data streams, and some must keep working when the network is weak or the budget is tight. Those pressures are what make edge AI attractive in living systems. Latency Becomes a problem whenever the system must answer while the action is unfolding. If the person is speaking, the patient is moving, the vehicle is approaching, or the animal is entering frame, a cloud round trip can be too slow to help. Bandwidth is the second pressure. Raw sensor streams are large, especially from remote places, so sending only the event, feature, or alert is much more practical than uploading every sample. Reliability and cost matter just as much. Networks fail, batteries drain, and cloud bills grow. So a device that can still make a useful decision on its own is usually easier to run for the life of the product. In these applications, privacy, speed, and resilience are not extra benefits. They're the reason the design chooses the edge in the first place, because the product has to work under real constraints, not ideal ones. Capability alone does not decide whether a system is acceptable. The way it is deployed matters more, because the same sensing power that helps a user can also be turned into surveillance or unfair monitoring. A monitoring system can cross the line if it watches people more than it serves them. Bias can also enter when a classifier works unevenly across body types, ages, environments, or species, and the same concern applies when a conservation camera or workplace sensor is repurposed beyond its original purpose. The deeper risk is opacity. When people cannot tell what is being recorded, why an alert happened, or who can see the output, trust breaks down, so responsible deployment needs purpose limits, validation, and a serious review of misuse cases. Employers in this space are not only buying model accuracy, they need people who can build the whole system, from sensors and inference placement to privacy, robustness, and failure handling. The work spans wearables, smart homes, health tech, conservation, agriculture, and safety systems. A strong practitioner knows how to integrate sensors, choose where inference belongs, and deploy under messy conditions while still respecting trust, compliance, and operational limits. A useful habit is to ask three questions: what must happen immediately, what can remain local, and what should never leave the device unless someone explicitly allows it. Those questions describe good engineering, but they also set the ethical boundary for the system. Edge AI becomes compelling when the target is alive, moving, private, or spread across places with weak connection. The opportunity is real, but so is the responsibility, because the same systems can be misused for surveillance, error amplification, or other harms if the design does not set clear limits. Edge AI often matters most when it reshapes a stream rather than choosing a label. The important idea here is that the output itself can be the product, whether that output is cleaner, safer, cheaper, or easier to use. A model at the edge does not always sit there making a final decision. It can take one signal and turn it into another one that better fits the situation, like cleaning audio, protecting privacy, or reducing the amount of data that has to move around. The useful shift in thinking is from questions to transforms. Instead of asking only what something is, we ask how the signal should be changed before anyone stores it, transmits it, or uses it downstream. That distinction separates classification from transformation. Classification ends in a label, but transformation ends in a new version of the stream, and that new version may still look like video, audio, text, or sensor data. This fits naturally with older embedded signal processing work. Devices have long filtered noise, compressed data, stabilized motion, and cleaned up measurements. Learning just gives the system a way to learn that transform from examples instead of relying only on hand-built rules. That is why these applications are so practical. A person cares that the call sounds clearer, the camera hides the room behind them, or the sensor reading is useful enough to act on, even if the model's internal step never gets seen. These workloads belong near the source because the signal is already there and the cost of moving it can be high. Latency, bandwidth, privacy, and reliability all become part of the design problem as soon as the data has to leave the device. Stream data is where the constraints show up fastest. Large video feeds are expensive to ship. Delayed responses can make a system unusable. Poor connectivity can break the pipeline, and sensitive data may never need to leave the device at all. Local processing solves a lot of that pressure. The device can reshape the signal first, or it can do the whole job locally and avoid sending the original stream anywhere else. Background blur makes the idea very concrete. The model is not trying to identify a scene for its own sake. It is trying to rewrite the image so the person stays visible and the surrounding detail becomes less exposed. Video conferencing is a good example because the result is visual, not textual. The system segments the person from the background and then renders a new frame where the foreground remains clear while the rest is softened or replaced. All the blur pressures point the same way here. If segmentation happens locally, the device can blur before transmission, send less visual detail, stay responsive on a weak network, and keep control over raw background data. That pattern still has limits. A blurred image can leak information, and a poor segmentation model can fail in ways that are obvious or harmful. So the technique is useful, but never a blanket guarantee. The same transform pattern shows up across many kinds of signals. Once you start looking for it, audio, speech, vision, text, and time series data all begin to look like versions of the same problem. The details change, but the structure does not. Each stream can be cleaned, masked, compressed, or reconstructed before it is used anywhere else. Audio systems can remove noise or echo. Speech systems can transcribe or convert voices. Vision systems can sharpen or stabilize. Text systems can redact sensitive parts, and sensor systems can fill gaps or detect anomalies. In each case, the model is changing the stream into something more useful. A better mental model is to group these by the kind of transform they perform, not by the industry they serve. Once the output is more actionable than the raw input, the edge device has done its job as a transformer. Virtual sensing makes the transformer idea even clearer. Instead of installing an expensive physical sensor, the device can infer that missing measurement from signals it already has. The basic trick is to combine cheaper measurements and learn how they map to the value you actually want. That can reduce cost and power while still giving a reading that is good enough for the task. Monocular depth estimation is the standard example. A single camera image can be used to infer approximate distance, which is not the same as direct range sensing, but can still be useful when cost or packaging matter. That trade-off is exactly why this belongs in Edge AI. On-device inference can make a product cheaper and easier to build while substituting for hardware that would otherwise be too expensive, too large, or too power-hungry. A transform can be useful and still be risky. The hard part is not only making the output look good, but making sure the system is valid, bounded, and honest about what it can actually do. A system can blur too little, reconstruct too confidently, or behave well in a demo and poorly in real use. Those failures matter because a transformed signal can give a false sense of correctness. The deeper point is that being able to transform a signal does not make the deployment ethical or safe. The same technique can support privacy, but it can also hide surveillance or overstate measurement quality if nobody sets clear limits. That judgment is a valuable skill across consumer devices, wearables, smart sensing, and industrial systems. Good engineers do not only build models. They decide what kind of model the product actually needs and whether the hardware and risk profile can support it. So the core idea is straightforward. A lot of edge AI exists to turn raw signals into better ones. That makes transformation a central application family, and it deserves the same care in design, validation, and deployment as any other edge system. Edge AI becomes easiest to understand when the model is treated as a signal transformer. The important question is not only what it predicts, but what new signal it can produce under real constraints. That shift changes the goal of the system. Instead of waiting for a label, the device can clean, mask, compress, or reshape the data so the result is immediately useful to a person or another machine. A background blur in a video call, a health indicator from vibration data, or speech turned into text are all examples where the transformed signal is the experience people care about. The model is not just classifying inputs, it is doing visible work inside the device. The modality changes, but the pattern stays the same. A local model can denoise speech, blur video, redact text, forecast equipment behavior, or synthesize a missing measurement when the edge device has the right context and limited resources. Those constraints are often the reason edge processing exists at all. If a response must be immediate, if data is too heavy to stream continuously, or if connectivity is unreliable, local transformation becomes the practical choice. That pipeline shows several benefits at once. The device segments the person from the room, applies the blur locally, and avoids exposing the unmodified scene, which helps privacy while also cutting delay and transmission load. This is synthetic sensing. The model infers a missing physical quantity from cheaper signals that already exist. With a single camera, for example, depth estimation produces a usable depth signal for navigation or scene understanding instead of another image. That is the product design question behind the technology. The strongest team connects model capability to latency, power, privacy, connectivity, safety, and cost, because feasibility alone does not make a device worth shipping. A transformation can be technically possible and still be a bad deployment. The next step is to look at what can go wrong when a system is accurate in the lab but limited, fragile, or misused in the real world. A model may blur away useful detail, reconstruct a signal with more confidence than it deserves, or behave well only on narrow test data. The risk grows when the same pipeline is reused in surveillance or monitoring settings where the stakes are high. A system can look fine until edge cases appear or operators trust the output too much. When a transformed signal drives a safety, hiring, or surveillance decision, quiet systematic errors matter just as much as obvious failures. Useful edge AI is not only accurate, it is appropriately limited and tested under realistic conditions. The real question is whether the transformation belongs in that place for that reason and with a clear understanding of who is affected by it. That checklist keeps the design grounded. It forces a team to think about where the transformation happens, how it behaves in practice, and what damage could follow if the output is delayed, manipulated, or simply incorrect. That is the central idea to carry forward. The most valuable edge systems do more than predict labels. They turn raw signals into something safer, cleaner, or more useful, and they must do it with care. Responsible design asks whether an edge system is not only accurate, but trustworthy in the real world. The focus here is how ethics, constraints, and deployment conditions shape whether a model deserves to be used. Trustworthiness comes from more than a good model score. It comes from a system behaving in ways that match the people, places, and risks around it. A model can look excellent on paper and still fail in practice once real conditions show up. Responsible design means fitting the system to users, constraints, and values, so the result is useful and defensible. That pressure is stronger at the edge because the device is physically close to the environment and the consequences. Temperature, connectivity, maintenance, and changing local behavior all become part of the design problem, not exceptions to it. A system can be useful and still be the wrong choice if it ignores safety, privacy, energy use, or long-term maintenance. The question becomes whether the benefit is worth the full cost of operating it. Non-functional requirements often decide whether a deployment succeeds. A small gain in detection is not enough if batteries die too quickly. Sensitive data leaves the device, or the hardware becomes too expensive to maintain. When processing stays on device, the design may protect privacy or reduce latency, but it also creates obligations around storage, updates, and alert quality. Responsibility follows the architecture, so the team has to account for every new duty it creates. Different groups will prefer different outcomes, and that is normal. The important part is making those preferences explicit so the team can design with them instead of pretending they do not exist. One user may want privacy even if it costs more. Another may care more about simplicity, lower power, or fewer service visits. Neither priority is wrong. The design has to reveal the trade-off honestly. A conservation agency, a factory, and a maintenance crew may all want different things from the same device. If those differences stay hidden, they come back later as rework, mistrust, or misuse. Data builds the model, but it also reveals what the team noticed and what it missed. That makes data quality an ethical issue as well as a technical one. Training data is the raw material of learning, and missing or skewed cases shape the model's blind spots. If the data leaves out important conditions, the system learns a narrower version of reality. Evaluation tells you whether the model will survive the field conditions it actually faces. A result from a convenient test set can look strong while hiding failures that appear as soon as the device leaves the lab. A clean test bench can create false confidence. The real lesson is that performance numbers mean little if they were measured in conditions unlike the ones the device will actually meet. A team can train and test on tidy samples from one place and one season, then ship into a much harsher environment. Rain, glare, drift, and storms can change the signal enough that the original evaluation no longer predicts behavior well. Many unfair outcomes start as missing, narrow, or location-specific data. Long before anyone discusses discrimination, the system may already be learning an incomplete version of the world. Data always comes from somewhere and sometime, so it cannot automatically represent every future situation. Those limits matter because a model can fail simply by being trained on a slice of reality. If one season, one site, or a few common cases dominate the data, the model may miss floods, droughts, or rare failures. That is bias in a practical sense. The system's view of reality is warped before it even makes a prediction. Fairness is not a fixed formula. It depends on who is affected, what the decision does, and how much harm a mistake can cause. A false alarm may be harmless in one setting and dangerous in another. If an error sends people into risky conditions or penalizes the wrong group, the same pattern of behavior becomes a fairness problem. The important question is who the stakeholders are and what each one values. A system is not fair just because it works for one group. The design has to make the trade-offs explicit and support the choice being made. Before deployment, the team needs a disciplined set of questions. That keeps ethics connected to engineering instead of leaving it as a vague afterthought. These questions force the team to check users, location, risk, data, evaluation, stakeholders, and misuse before the system goes live. They turn responsible design into something concrete enough to act on. A system often affects more people than the direct user. Operators, residents, regulators, and bystanders can all carry consequences even if they never touch the device. Location changes everything from sensor quality to model behavior. Weather, power, maintenance access, and local patterns all shape whether the device behaves well. Failure is not only about incorrect predictions. A late alert, a missing reading, or a tampered signal can be just as damaging as a bad classification. Every data set carries omissions. The team has to ask which rare cases, environments, or populations are missing, because those gaps often become real-world failures later. A convenient test bench can produce confident but misleading results. The evaluation has to reflect the field, or the number on paper will not mean much in practice. Those priorities do not line up the same way for every group. Making them explicit helps the team choose a design that is acceptable to the people who live with its consequences. A system can change meaning after deployment if someone uses it in a new or harmful way. Good design anticipates that possibility instead of assuming everyone will use it as intended. Limits need to be explicit so no one mistakes the device for something it cannot do. Clear boundaries reduce overtrust and make the product safer to use. Misuse is a design concern, not a surprise. A tool built for infrastructure can be redirected toward surveillance or evaluation unless the team puts real limits and safeguard around it. Responsible design is part of the engineering, not an extra layer added afterward. It is also a real professional skill, because teams increasingly need people who can connect model performance to harm, limits, and deployment reality. That habit keeps the analysis grounded. When you can judge those limits clearly, you can decide whether an edge system is not only capable, but actually responsible. Responsible design becomes part of the engineering work once an AI system leaves the lab, because every choice now has consequences for real people and real use. The goal here is to see ethics as something that shapes whether a system can be trusted and deployed at all. Responsible design belongs inside product quality, not after it. A system is not done just because it works in a demo. It has to be safe, private, reliable, and appropriate for the setting where it will live. Once the system leaves the lab, the question changes from, can it produce a plausible answer, to can people trust it in the real environment? A model can be accurate and still be a bad product if it is invasive, brittle, discriminatory, or misleading under actual conditions. That is why requirements like privacy, safety, latency, reliability, energy use, cost, explainability, and misuse resistance matter so much. They decide not only how to build the system, but whether a particular version of it should be built at all. Design choices are always a negotiation among values, because different settings prioritize different outcomes. The same technical architecture can be acceptable in one context and unacceptable in another when privacy, safety, equality, or sustainability matter differently. Lower latency can reduce harm in one case, but it may require more power or more local storage. On-device inference can protect privacy, while remote monitoring may improve efficiency but increase data collection pressure. The right answer depends on which value matters most in that setting. Different people are affected in different ways. Builders, users, subjects, payers, and people who live with the failures. A shared process has to name those interests, identify plausible harms, and set limits clearly, because performance alone never tells the whole story. The ethics of an edge AI system start with the materials used to build it. Data, labels, and evaluations set shape what the model learns, what it misses, and how confidently it fails. Training data behaves like construction material, not a guarantee. If the data is narrow, noisy, or imbalanced, the model inherits those limits and learns a distorted view of the world. Coverage tells the model what kinds of cases exist, labels tell it what those cases mean, and balance determines whose examples are represented often enough to matter. When any of those are weak, the system may look well trained while actually carrying blind spots from the start. A model can perform well in development and still break down once the environment changes, such as on a factory floor with poor lighting, dirty surfaces, or rare defects. The same problem appears when underrepresented people or uncommon conditions are left out of the data, because those gaps become real failures for the people affected. Evaluation data is only useful when it measures the same conditions the system will face after deployment. If the test set is too clean or too convenient, the numbers can look precise while the judgment is still wrong. A valid test needs realistic conditions, enough samples to reveal weak spots, and metrics that match the actual task. A model that looks strong on curated footage can still struggle with glare, blur, packet loss, or weak connectivity, so the measurement has to reflect the real room, not an ideal one. Historical data also goes stale because the world changes after collection. Populations shift, hardware changes, and incentives change, so a model can drift away from reality without any code being touched. That is why monitoring has to continue after launch. Bias and fairness are not abstract labels. They describe how errors land on real people. The same model can be acceptable in one context and harmful in another, depending on which mistakes are most dangerous and who carries the risk. Bias is a systematic tendency to miss the mark in a way that matters, and discrimination is what happens when those misses fall unevenly on groups. In safety systems, misdetections may be the worst outcome. In hiring, even small, unequal error rates can become harmful. In public devices, opacity itself becomes a risk because no one can challenge the result. Before deployment, the team needs to know who uses the system, where it operates, what can go wrong, and who can notice or appeal when it does. Those are design requirements, not philosophical extras, because they determine whether the system can be used responsibly at all. A deployment checklist turns these ideas into questions the team can answer plainly. The point is to make responsibility concrete before the system is shipped. A serious team should be able to explain the system without hiding behind jargon. If the answers are vague, the risks are probably still vague too. Data reviews should ask who and what are missing, because missing coverage becomes missing reliability. If certain environments or groups never appear in the data, the system will be weaker exactly where it needs to be strongest. Model review means naming both strengths and failure modes. A system is only ready when the team knows its limits well enough to explain when it should not be used. Users and affected stakeholders often judge value differently from the engineering team. Their view matters because a technically impressive feature can still be harmful if it creates stress, surveillance, confusion, or unfair burden. Testing has to happen in conditions that resemble actual use, not only in a controlled lab. If the device, environment, or workload changes, the evaluation has to change too, or the result is misleading. Misuse often appears after release, when someone finds a new way to use the product that the original team did not intend. Good design anticipates repurposing, surveillance, gaming, and other off-label uses, then builds limits and safeguard around them. A helpful tool can become a monitoring device. A safety camera can become a surveillance system, and a privacy feature can be turned toward concealment. That is why safeguards and governance have to be part of the product design, not an afterthought once the harm is already visible. For product engineering, applied research, ML ops, and safety review, the real skill is translating model performance into deployment readiness. The strongest systems are not just impressive in demos. They are defensible in the field because their limits, risks, and human costs have already been confronted. Edge AI raises two linked questions. Can the device be trusted, and can its decisions be checked after deployment? That matters because once the model lives inside a product, the cost of being wrong moves into the real world. A model can make a prediction and still fail the moment people need to rely on it. The deeper issue is whether anyone can verify the decision, understand the failure, and respond when the device is wrong in the field. A black box means the inputs and outputs are visible, but the reasoning in the middle is hidden. That hidden middle is what makes debugging and accountability difficult. The device may accept sensor data and produce a decision, but the path from one to the other is hard to inspect. In Edge AI, that opacity often comes from embedded models, proprietary software, and missing access to the raw data needed to explain a failure. That difference matters because the system sits in a room, on a road, or inside a body, where other people may depend on it or be affected by it. When something goes wrong, the team may not have enough evidence left to reconstruct the event. If sensor data is not kept or cannot be exported, a bad inference leaves little behind to inspect. Then you know an output happened, but not whether the input was wrong, the signal was misread, or the case was simply outside the training experience. A useful example makes the risk concrete. A deployed device can appear healthy while quietly missing the events it was meant to detect. The failure stays hidden because the output still looks orderly. A remote monitor may report tidy totals and still be undercounting badly. If the system is placed near the sensor to save bandwidth, the local output can look fine even while the real-world count drifts away from reality. The cause might be lighting, sensor drift, or a model that never saw enough real conditions. The damage is larger than the technical miss because decisions were already made using incomplete evidence. That combination is the danger. The device fails quietly, and the record is too thin to expose the problem quickly. By the time someone notices, the error has already shaped actions in the field. Edge deployment adds extra barriers to inspection, even when the same model might be easier to study in a centralized setting. The more autonomy the device gets, the less of its reasoning is visible from the outside. The model may sit inside a sealed appliance, and the vendor may not expose internal features or confidence scores. Network limits and privacy design can also prevent raw observations from ever leaving the local environment. Keeping data local can be the right design choice, but it has a cost. The system becomes harder to inspect, so a mistake can vanish behind a result that looks clean and convenient. People often trust an on-device system too quickly because it feels familiar and self-contained. Fast, local responses can still lack the safety evidence needed to prove they are dependable. One partial answer is to make the system easier to examine, but that always comes with trade-offs. Any added visibility has to be paid for in storage, bandwidth, complexity, or privacy. If the system can show which signals mattered, report confidence, or keep a useful audit trail, it becomes easier to question and improve. The cost is that more logging uses resources, more interpretable models may lose accuracy, and richer diagnostics can create new privacy risks. Explainability should be treated as one design choice among several. Sometimes a simpler model with a clear failure mode is safer than a complex one that nobody can inspect. And sometimes the right move is to narrow the task instead of adding more explanation. Bias is not only about prejudice. It is often about mismatch between the model's world and the real one. That mismatch can enter through design, data, algorithms, and testing. A system can be biased even when nobody meant harm. The core issue is that the training and testing assumptions do not line up with the situations the device will actually face. Human bias enters through assumptions about users and context. Data bias comes from unbalanced training coverage. Algorithmic bias from methods that amplify or smooth signals unevenly, and testing bias for validation that misses important cases. A test set can look broad and still fail to include the one scenario that matters most. When that missing case is expensive or inconvenient to simulate, the deployment can pass review with a false sense of confidence. That is a structural risk whenever real-world testing is costly. Teams are often tempted to measure the cases that are convenient, while the cases that matter most remain under-examined. A responsible deployment starts by defining the safe operating range and being honest about what lies outside it. The team needs clear boundaries for inputs, environments, uncertainty, and human fallback. The practical goal is not perfection. It is clarity about where the device is reliable, where it is uncertain, and when it should refuse to act or hand control back to a person. That judgment is part of engineering, not an afterthought. If the system cannot be inspected, validated, and constrained enough to avoid silent harm, the right decision is to redesign, narrow the use case, or stop. The people who matter here are not only model builders. Product engineers, ML practitioners, operations teams, and safety reviewers all need to document assumptions and define test boundaries so the system can stand up after the demo is over. An edge AI system earns trust only when its behavior can be checked, its limits can be stated, and its failures can be contained. Without that, deployment is premature. Edge AI becomes risky when the model disappears inside a product and its decisions are hard to inspect or challenge. The main questions here are who gets affected, how bias enters, and what limits have to be in place before deployment. Edge AI is often less a modeling problem than a deployment problem. Once inference moves into a device, the environment, the users, and the failure modes all become part of the system. A model that looks fine on a developer's desk can become opaque once it is embedded in a phone, camera, vehicle, or appliance. At that point, people rely on behavior they cannot easily see, and that makes mistakes much harder to catch or fix. Field conditions rarely match the lab. Lighting changes, sensors drift, noise builds up, and users behave in ways the team did not predict, so a model that looks stable during testing can weaken quickly in practice. Failure reaches beyond the buyer of the device. The harm can land on users, bystanders, and even the developers who have to diagnose a system they can no longer fully observe. A bad decision from an edge device can cost someone money, time, safety, or trust. When a system acts on people who never chose to be part of its environment, the impact spreads to bystanders as well as customers. Developers need evidence to understand why a decision happened, but black box deployment often strips that away. If the device throws out the audio, image, or sensor stream after inference, the team may know a result happened without knowing whether the input was bad or the environment was outside the model's range. Explainability can make behavior easier to audit, but it always comes with a cost. The question is not whether explanations are nice to have. It is whether the extra visibility is worth the extra load on the system. A heat map or feature summary can show that the model is focusing on the wrong cue or missing the right one. Still, those tools may demand more computation, more memory, or more instrumentation, and that can hurt latency, battery life, or simplicity. Bias enters edge systems from several directions, not just from the data. Design choices, training coverage, model choice, and testing strategy can all shape who the system works for and who it misses. It helps to break bias into separate sources because each one needs a different fix. Some problems come from assumptions, some from data, some from the algorithm itself, and some from how the system is tested. Designers often build for the user they imagine, not the full range of real users. If they assume one accent, one body type, one distance, or one behavior pattern, the product will quietly exclude everyone outside that narrow picture. A model can only learn from what it sees, so unbalanced data creates blind spots. If the dataset overrepresents one setting or one group, Performance can look strong in testing and fail when the missing cases appear in the field. Sometimes the issue is the method itself. An algorithm may reward convenient patterns, punish uncertainty unfairly, or interact badly with the task in a way that harms certain groups or edge cases. Narrow evaluation is dangerous because it makes the system look safer than it really is. If testing covers only easy or common cases, the rare failure that matters most may be the one that slips into deployment. A package monitoring model might perform well on clean, standard shipments and still fail on a partially obscured label in bad weather. That is the pattern to watch for. The system passes the routine case and then breaks on the one situation that actually matters. Two deployments make the risks easy to see. One where a human fallback is treated as if it were guaranteed, and one where the environment makes later debugging nearly impossible. In a self-driving system, it is unsafe to assume a human can always rescue the machine instantly. Attention drops, reaction time is limited, and a fallback that exists only on paper can create confidence without real safety. Remote wildlife cameras and similar devices may lose the very evidence needed to debug them. If the raw image is gone or the connection is intermittent, the team may know a label was produced, but never learn whether the image was blurred, blocked, or simply misread. Responsibility in edge AI starts with boundaries. The system needs defined operating conditions, clear expectations for input quality, and a plan for when it must stop, escalate, or refuse to act. Some projects are not just risky. They are inappropriate to deploy at all. The decision to stop is part of professional judgment, not a failure of ambition. Responsible deployment needs domain knowledge, relevant data, the right algorithm, and enough validation to match the real world. When those pieces are missing and safety still cannot be established, the correct choice is to refuse the deployment rather than patch over the gap. Employers value people who can judge whether a system should ship, design tests around the actual environment, and explain limits without hiding behind jargon. Good teams do not just build models. They place them carefully and define what they must never be asked to do. That final standard is the practical one. A deployment has to be visible enough to inspect, reliable enough to trust in the field, bounded enough to control bias risk, and designed so that failure does not depend on perfect human response. Edge AI can reduce delay and keep data local. But those same traits can also make monitoring easier to hide and harder to challenge. The question here is not whether the system works technically, but whether its deployment creates harm for the people being watched. Keeping inference on the device can protect privacy, but it can just as easily support persistent monitoring. When a system is fast, autonomous, and low bandwidth, it becomes attractive for constant tracking, even in places where people never agreed to be observed. Ethical harm depends on where the system is used, who it affects, and what power it gives to the wrong actor. A model can be well engineered and still become unacceptable once it is placed into a real setting. A system can score well on accuracy and still treat some groups unfairly. That happens when a model reflects data gaps or social assumptions that make accent, disability, or communication style count against a person in a decision they cannot easily contest. Once a device is embedded in a workplace, home, or public space, the setting changes what the system means. Even a correct prediction can still violate consent or dignity if the surrounding use is intrusive or discriminatory. Bias can enter at several stages, so the source of harm is not always the model alone. People, data, assumptions, and tests can each push the system toward unfair outcomes. A useful way to think about bias is as a chain of decisions. Each stage can quietly narrow who the system works for and who bears the cost when it fails. Teams often miss danger when they imagine their own experience instead of the user's. If no one on the team would feel watched or screened by the product, they may underestimate how invasive it feels to everyone else. Training data that misses part of the real population produces uneven performance. The model then looks stable on paper while becoming less trustworthy for the people it saw too rarely during training or calibration. A design can bake in a proxy signal that seems convenient but actually tracks the wrong property. Once that happens, the model may treat correlation as if it were ability, trustworthiness, or intent, which is a serious error in decision-making. clean evaluations can hide problems that only appear in messy real use. If the test environment is too short, too tidy, or too similar to the lab, the system may fail in ways the evaluation never revealed. Hiring systems are a strong example because they can appear efficient while still encoding hidden bias. Accent, lighting, camera quality, disability, and cultural norms can all shape the score, and the person affected may never know why they were judged that way. Misuse is not a corner case that can wait until after launch. If a product can be repurposed easily, the team has to think about that use from the start, not after someone else has already turned it into a tool for harm. A system built for one purpose can become risky in a different hands or a different setting. Wildlife tools, safety monitors, and other edge devices can all be turned towards stalking, concealment, or unauthorized tracking once deployment moves beyond the original plan. That question forces the team to think beyond the intended customer. If the answer includes covert profiling, intimidation, illegal capture, or stalking, then the product needs stronger limits or may not belong in the world at all. Harm can come from carelessness, from predictable misuse, or from a culture that makes it hard to speak up. That wider view matters because not every failure is a simple mistake in the code. A team can ship without thinking through impact. A customer can use the system in a foreseeable harmful way, or someone inside the company can notice danger and stay quiet. All three produce real damage, even when only one of them looks intentional. When engineers, product managers, or designers cannot raise concerns safely, problems stay buried until they become public failures. A healthy team needs room for uncomfortable feedback before the product hardens into something hard to change. Good intentions are not enough here. Mitigation has to be concrete and enforceable. The useful question is which practices actually reduce the chance of preventable harm. Mitigation means building habits and controls that make bad outcomes less likely. It includes team structure, review processes, outside scrutiny, and real limits on how the system can be used. Diverse teams are more likely to catch assumptions that a uniform group would miss. Different life experiences make it harder for blind spots to survive unchallenged. People need to be able to raise concerns early and concretely, without fear of punishment. If the culture discourages dissent, the first honest warning may arrive after the damage is already done. Review has to match the real setting, not just the lab. Risks can change after deployment, so the team needs to check the system both before release and after it starts operating in the wild. Outside review can expose problems that internal teams miss or normalize. An audit is especially useful when the product touches sensitive decisions because it adds another layer of accountability. Rules and contracts can help when they genuinely limit what others can do with the system. They're not perfect, but they can slow abuse and make misuse easier to challenge. External controls can reduce some abuses, yet they cannot rescue a product whose core purpose is already troubling. A team still has to decide whether the deployment itself is acceptable, not just whether a policy document exists. There is no universal measure of ethicality. The real test is whether the system fits the values of the setting, the power relationships around it, and the practical impact on the people who live with it. Building or buying edge AI now requires judgment about misuse, fairness, and accountability, not just model performance. Teams need people who can evaluate trade-offs and protect the product from becoming dangerous in practice. Every deployment needs the same hard questions. Who could be harmed, how the harm happens, whether concerns can be raised honestly, and what safeguards can actually be enforced. If those questions feel uncomfortable, that usually means they matter. Edge AI can protect privacy in one setting and become a tool of control in another. The placement of the system, the people it observes, and the decisions it supports determine whether it serves people or harms them. When intelligence moves close to people and places, the ethical stakes change fast. Keeping data on the device can lower delay and preserve privacy, but the same setup can also make surveillance easier and errors harder to notice. The first risk shows up right where the data is collected. Once a device can see, hear, or identify people locally, it can protect them or violate their rights depending on how that sensing is used. A local model that filters data before it leaves a room can be a privacy safeguard. But if the same model identifies people or tracks behavior, The device becomes a quiet surveillance system with very little transparency or consent. Putting inference on the edge does not remove the social meaning of being watched. It changes who can observe, how long observation can continue, and whether the people affected have any real way to refuse. The second risk comes from systems that look objective while quietly reproducing human bias. Automation can narrow opportunity when the features and testing choices reflect the builders more than the people being judged. Hiring models can pick up speech patterns, facial movement, accent, or camera quality and treat them as if they were job signals. Those features often stand in for disability, culture, neurodiversity, or social background, so the model can discriminate without anyone writing a rule that says to do so. The harm is easy to miss when the tool is framed as decision support. If the model acts like a filter instead of one input to judgment, it can quietly block qualified people while product teams mistake the presence of software for rigor. The third risk is failure through carelessness rather than intent. A system that was never tested in the real conditions it will face can become dangerous as soon as people rely on it. A demo can look fine and still hide major weaknesses. Once the device enters noisy or safety-sensitive environments, missed edge cases and silent failures can do real harm. That is why go or no-go review matters. Teams need to ask whether the model works across real contexts, whether failures are visible, and whether users can recover when the device gets it wrong. The fourth risk is repurposing. A system built for one good purpose can be turned toward harm when other users find a way to bend it to their own incentives. A wildlife camera designed for ecological study can help researchers track species and reduce manual review. The same hardware can also reveal patrol routes or animal locations, which is why the original intent does not guarantee safe use. If a device can expose raw feeds, reveal sensitive locations, or bypass safeguards, then the design is incomplete. Developers need to think about who else wants the capability, what they gain from misuse, and how far the system can be pushed before it becomes harmful. Avoiding these failures takes more than a better model. The real protection comes from people, process, and repeated review that can catch risk before it hardens into product behavior. Different backgrounds make blind spots easier to see because people notice different kinds of risk. That only works when someone can raise a concern early without being punished for slowing the release. Review cannot happen once and then disappear. New models, new deployments, and new customer groups can all change the risk profile of the same system. Audits, licensing terms, and use policies can limit some misuse and expose missing documentation or testing gaps. Still, none of those tools can make a harmful deployment acceptable on their own, and none of them resolve the deeper question of consent or legitimacy. Responsibility around Edge AI now sits inside product work itself. Engineers have to think across technical, legal, and social concerns because these systems ship into real environments where all of those pressures meet. Accuracy and latency are not enough on their own. A system is only ready when the team can explain who may be affected, how it could fail, how it could be repurposed, and what protections are actually in place. That checklist becomes a habit rather than a one-time reminder. As the product matures, these questions keep changing, and staying alert to them is part of deploying Edge AI without turning useful sensing into avoidable harm.